Good morning, folks. Today we're going to learn about conservation of momentum. We're going to see that there's a law that's associated with this concept. We're going to introduce the concept. We're going to look at different types of collisions and how conservation of momentum applies to those. And then finally, we're going to see an equation where we can actually manipulate this and do some calculations using this concept of conservation of momentum. So where we're going to start here is imagining a cannon firing a cannonball. Now, we know from our study of the third law that the force on the ball is the same as the force on the cannon as we fire the thing. Forces are equal in magnitude but opposite in direction. So the ball is being pushed forward to our right and the gun is being pushed backwards to our left. Now, we're going to assume for a moment that the gun has a mass of 1,000 kilograms and the ball has a mass of 2 kilograms. We want to figure out how fast the ball is moving when it leaves the barrel. Now, obviously, we need a little bit more information for this. So we're going to assume that the force acting on both the ball and the gun is 1,000 newtons. And we're also going to assume that the ball takes 1 second, 1 full second to travel down the barrel of the cannon. Now, obviously, that's unrealistic, but we have a concept here, and this makes the math a little bit easier. So I want you to pause the video in just a moment here, and I want you to do this calculation. I want you to figure out what is the speed of the ball when it leaves the barrel. Give you a hint, you're going to use the impulse equation. I would like you to have this memorized, okay? So know it well enough that you don't need to look it up every time. So at this point, pause the video, do the calculation, and figure out how fast the ball is moving. Okay, unpause it at this, well, yes, so you can, I'm going to tell you the answer now. So if you haven't paused it, you need to pause it so you can work it out yourself. But what we're going to do here is we're going to put in 1,000 for the force. That's the F is the force, so 1,000 for the force. 1 second for T. The mass of the ball is the one we're interested in, so that's going to be 2 kilograms. We solve for V, and it turns out to be 500 meters per second. That's the answer you're going to get. Okay, now we want to do the same thing for the gun, for the cannon. So you're going to set it up the same way, except that you're going to use 1,000 kilograms for the cannon. And do all the same. So pause it, figure it out. Okay, if you haven't paused it, do it right now because I'm going to show you the answer. It comes out to be -1 meter per second. And we put the negative in here because we know that the cannon moves to the left. So if we're doing right direction as positive, we know just from our experience that the cannon's going to go to the left. So we're going to call that a -1 meter per second. Okay, so that's kind of review from last time, but now we're going to take it a step further. Now I want you to calculate the momentum of the cannon, that's the gun, and the momentum of the ball. And remember, this is our equation for momentum, P equals mv. Momentum is equal mass times velocity. We have the velocity of the ball, the velocity of the cannon, so you can figure them out. Pause it for a moment so you can get those numbers. Okay, I'm going to reveal the answer here in a moment, so pause it if you haven't already. And here are the answers. We wind up with 1,000 kilogram meters per second for the ball, moving to the right, and -1,000 kilogram meters per second for the gun, which is moving to the left. Now, it might strike you as a little bit strange that these numbers seem to be so similar, but it's not. It turns out that it has to be this way. Okay, now, what we are seeing is that the total momentum, if we add together these momentums, which we can do because they're in the same units, kilogram meters per second, if we add the total momentum together, we get a total momentum for the gun and the ball of 0. 1,000 minus 1,000 is 0, no momentum. And this actually kind of, well, maybe it's surprising, maybe it's not, but if we think about it, if we consider the momentum of the system, which is the gun and the ball, if we consider the momentum of the system before we fired it, nothing was moving. The gun and the ball were just sitting there and it had no momentum. So before we fired the cannon, the system had no momentum. The momentum was 0. And after we fired the cannon, each piece did have some momentum, but when we added the momentums together, then there was still no momentum. The net momentum was 0. What we see is that the momentum was in this system was conserved. That's what the law of conservation of momentum says. It says that the net momentum of a system never changes. So the system was the gun and the ball. And before we fired the cannon, it had no momentum. And after we fired the ball, the momentum was conserved. The total amount of momentum was the same. That's what we mean by this word conservation. It means that the total amount never changes. And the total momentum after we fired it, the total momentum of the system was still the same. It never changed. So a system is a group of objects that interact with each other in some way without any forces acting from outside the group. That applies to this case. There's nothing pushing on the cannon. There's nothing pushing on the ball during the collision. It's just the cannon and the ball interacting with each other with no external forces. Okay? This is a biggie. You need to know it. Law of conservation of momentum. The net momentum of a system never changes. Okay, now we have to pause for a moment here and talk about different types of collisions, because it turns out there's two kinds of collisions. One type of collision is called an elastic collision, which is where objects bounce. And if we want to be technical about it, it's not just that they bounce, it's that they bounce perfectly, but with no loss of energy. Nothing heats up, nothing is deformed. It's a perfect transfer of energy, but the objects bounce. And for our purposes, we can say an elastic collision is where things bounce. And then an inelastic collision is where the objects stick together. So here we have a van which has run into a car and they're stuck together. That's an inelastic collision. Another example would be like a ball of putty that you throw at a bowling ball and the ball of putty sticks to the bowling ball and then they roll away together. Now, here's the important thing. Momentum is conserved in both cases. So the law of conservation momentum is always true. It is an absolute in the way that our universe works. So it doesn't matter if the objects bounce or if they stick together, momentum is conserved through that collision in both cases. Now, today we're going to look at elastic collisions, and next time we'll look at inelastic collisions. Today we'll look at what happens when things stick. But I want you to remember this. Momentum is always, always, always conserved in all collisions. That's the way our universe works. Doesn't matter if they bounce or if they stick. Okay, so we're going to look at, here we go. We're going to consider the cannon firing the cannonball again. And we're going to call the cannon itself, the gun, object 1, and the ball itself, object 2 for this purposes. Now, when we're doing calculations that apply this concept of conservation momentum, when we're doing the math, this is the equation we use. And it looks a little scary at first, but don't worry about it. It's actually very simple. M times V is momentum, mass times velocity, that's momentum. So what we're saying is the momentum of the first object, which is the cannon in this case, plus the momentum of the second object, which is the ball in this case. If we add up those momentums from before the interaction, before the collision, we can get a total momentum for that system before the interaction. And then we look at the same two objects after the interaction. So M1 V1 is the momentum of the gun after we fire it, and M2 V2 is the momentum of the ball after we fire the cannon. So let me show you how it looks when we plug some numbers into this. Same one. This side is the momentum of the system before we fire it. And since they're not moving, the velocity of the cannon and the velocity of the ball are both zero. That means there's no momentum. 0 plus 0 equals 0. So the net momentum before we fire it is 0. Now, after we fire it, we have 1,000 kilograms, that's the mass of the cannon, times some velocity. And we don't know what the velocity is, but that's what we're going to be figuring out. But the ball, object 2, has a mass of 2 kilograms, so that's M2 right there, plus the velocity of the ball, which we've decided is 1,200 meters per second. That's given to us. So this term here is the momentum of the ball. This term here is the momentum of the cannon after we fire it. But conservation of momentum says that when we add these two things together, it has to add up to 0. So what we do next is we go to, we make this 2 times 1,200 is 2,400. We move it over to the left side of the equation. So we get negative 2,400 is equal to 1,000 times V1, which is the speed of the cannon. And when we divide by 1,000, we find out that the cannon is moving at 2.4 meters per second in the negative direction. So the cannon recoils, moves to the left at 2.4 meters per second. Okay? So to summarize, we use this equation. Each term reflects the momentum of the first object plus the momentum of the second object before the collision. The second terms are the momentum of the first object and the momentum of the second object after the collision, which in this case is the cannon firing. And then you solve for the variable that you don't know. And that's all there is to it. Okay, let's do one more here. We have a bowling ball rolling at 9 meters per second, and it hits a bowling pin, which weighs 2 kilograms, and then the pin bounces away at 14 meters per second. So the bowling ball hits it real hard, it goes flying away. And what we want to figure out is the speed of the ball after it hits the pin. Now, intuitively, we know that the bowling ball is going to slow down some after it hits the pin, but we're going to use our equation here to figure out exactly how much. So let's go back to our camera. This is the given information. 7 kilogram ball, 9 meters per second, hits a stationary 2 kilogram pin that bounces away at 14 meters per second. We want to know how fast the ball is moving after the collision. So here's our equation for conservation momentum. This is before and this is after the collision. And they have to be equal to each other. That's what the law says. So we're going to call the ball object 1 and the pin object 2. And we have 7 kilograms times 9 meters per second plus 2 kilograms, that's the pin, times 0, because it's not moving, equals 63 plus 0 kilogram meters per second. And then after, we have 7 kilograms for the ball times some speed, that's what we're trying to figure out, plus 2 kilograms times 14 meters per second. That's the pin after the collision. So we get 7 times V plus 28, and those are equal to each other. So we're going to subtract 28 from both sides, minus 28, and we get 63 minus 28 equals 35. So we have 35 kilogram meters per second equals 7 kilograms times V of the ball. So we're going to divide both sides by 7 kilograms, and we get 5 meters per second equals the speed of the ball. You may want to watch that once or twice, but that's how we do it. We set up our equation for conservation of momentum. We plug in the values for each piece, ball before the collision, the pin before the collision, add them up, and we get a total momentum of 63. Then the ball after the collision and the pin after the collision. We have all the numbers for the pin, and we can solve for the speed of the ball. There it is, comes out to be 5 meters per second. All right, that's it for today, and we will see you next time.